So talking about these two energies, what would you rather be hit with? You know what watts are?
Yeah.
What is a watt? 100 watts.
Joules per second.
Yeah, a watt is a joule per second, so this would be 100 joules per second. And so if you're under a 100 watt light bulb, there's 100 joules of light being emitted per second. And so this boils down to this. What would you be under? What would you rather be under? A 100 joules per second, a 100 watt X-ray light bulb or X-ray bulb, or a 100 watt red light? Well, some people will say, well, you know, it's 100 joules per second, 100 joules per second, it's the same energy. Is it the same energy? No. 100 watts of X-ray is not the same as 100 watts of red light. Why is that? Well, if I asked you in 2 seconds how many joules, in 2 seconds I'm going to have 200 joules. So it's the same. It's going to be the same for both red and for X-ray. And so the thing that's different is this. This we call the total energy. We also have to look at one more energy, and what energy is that? The energy of a packet of light. And so what the packet of light, or the energy of the photon of light, and it turns out the X-ray photons, you know, 100 joules of X-ray photons versus 100 joules of red photons. 100 joules of X-ray photons, you have a few, you know. And here, 100 joules of red photons, you have many. And so the difference is like this. X-ray photons would be like a few bullets. And so let's say there's, maybe not a good analogy right now, but let's say if you shot bullets into a crowd, that's going to cause some serious damage, even if there's a few of them, right? A few bullets. Whereas red photons would be like styrofoam balls, you know, but you just have a lot more of them. You have a lot more styrofoam balls versus one bullet. Well, both have the same energy, because if you add up the cumulative energy of all these styrofoam balls, then it's going to be 100 joules, versus this one, which is just 100 joules by itself, right? And so yes, the total energy of both will be the same, except the bullet is going to cause a lot more damage. This would be the ionizing radiation part. So, I mean, this got me thinking about radiation. Some people, when they're thinking about radiation, they think about the total energy, the cumulative effect. And so when some people are talking about radiation, they don't qualify it as being X-rays or gamma rays. They just say it's this many joules. And so when they're talking, sometimes when people are talking about radiation, they're talking, well, that's equivalent to taking an airplane flight over. But, you know, there's certain things that are different in thinking about, you know, radiation. But anyway, getting back to this, this is called the photoelectric effect. And this is what won Einstein the Nobel Prize, the photoelectric effect, not his theory of relativity. And the photoelectric effect is described by this. It's by ionizing a metal. Metals are easy to ionize. Why? You got a metal, it's easy to ionize because metals have loosely held electrons. And so one metal that's very easy to ionize is something like potassium. Potassium can be ionized by visible light. And so if you have potassium metal, you don't want to expose it to visible light. You want to seal it in an amber or brown bottle. That way no visible light can hit it. Okay, you also don't want to expose it to air. But it turns out visible light will ionize it. And so we tried red photons. Not enough. Red photons just don't have enough kick or punch to ionize it. And so this would be red, or red light. But blue light will. Actually, I better do a different. Blue light, when blue light hits it, blue light's a higher frequency. Blue light hits this, electrons get excited, it knocks an electron off the surface. This is blue. So what we can do is we can try this. Let's say this is 100 watts. Of red. Let's bump it up. Let's go to 200 watts of red. If we do 200 watts of red, then we're going to get a lot more energy. Right. And so if we bump this up to 200 watts, amplitude increases. The amplitude is related to the total energy. And surely 200 watts should do it, right? No, it doesn't. And so we just keep bumping it up. Let's go to 500 watts, 1,000 watts, 2,000 watts. But no matter how high we crank up the power here, it doesn't ionize it because these are like styrofoam balls. And even if you have a tidal wave of styrofoam balls, the styrofoam balls aren't energetic enough to knock an electron off. Whereas for blue, if I crank up the blue to 150 watts, then I'm going to get even more electrons emitted. Right. I shouldn't say more. I should say the electrons emitted are going to be even more energetic, get knocked off with more force. And so the photoelectric effect is we got to keep track of the two energies. You know, we might only have 100 watts of blue, but that doesn't mean 100 watts of red will knock an electron off, even though they're equivalent in total energy. So when we're doing this, we have to be careful in our calculations. Do you know how much energy it costs to break a bond? How much energy it costs to break a carbon-carbon bond? Like in DNA? Bond energy is around 400 kilojoules per mole, but let me look it up and give you a more accurate number. Where's bonds? Chemical bonding, that would be chapter 10. I forgot to look it up this morning. Chapter 10 or chapter... $347. So let's do an example calculation. A carbon-carbon bond costs 347 kilojoules per mole to break. We're going to ask the question, what is the minimum energy? What is the minimum energy? Well, the minimum energy is 347 kilojoules, right? If If I don't have 347 kilojoules, I'm not going to break the mole bonds. And so if I'm thinking about minimum energy, then I'm thinking about what is the minimum energy, i.e. minimum frequency, because frequency is related to energy. Right? But if it's minimum frequency, then in terms of wavelength, is it the minimum wavelength? No, it would be the maximum wavelength because it's inversely proportional. And so what is the maximum lambda required to break the carbon-carbon bond? This is for light, maximum lambda light required to break the bond. And so let me do this here. So it's 347 kilojoules. And then I need some equations. The equations I have is the relationship between frequency and lambda is C is equal to lambda times nu. Lambda is in meters, the wavelength. Nu is the frequency. And the frequency is how many cycles pass by in a second. A cycle would be a peak to peak or valley to valley in the wave. And so peak to peak or valley to valley. How many wave cycles pass by a second? And so a cycle per second is also known as a hertz. And a hertz, sometimes we get rid of the cycle and just call it a seconds to the minus 1. And so all of these three are the same thing. And so we have meters per second, which is the speed of light. And then as far as the energy of the photon is given by this equation. That is the energy for the smallest particle or piece of that light, I shouldn't say particle, the smallest packet of light, is equal to h times nu, the frequency, which is equal to hc over lambda. H is called Planck's constant. Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. And so here, let's try to figure it out. It looks like lambda is equal to hc over the energy, right? And so h is 6.626 times 10 to the minus 34 joules times seconds. C is 3.00 times 10 to the 8 meters per second. E is 347 kilojoules, right? 347, this is in joules here, so let's do 347 times 10 to the third joules. So joules cancel out joules, seconds cancel out seconds, and gives us the wavelength in meters. And so let's calculate that, the wavelength in meters. Can somebody punch out the...
.76
times 10
to the negative 29.
Times 10 to the negative 29 meters. Okay. Then I look at the electromagnetic spectrum on page 297. Page 297, and I see 10 to the minus 29 meters. 29 meters is deep into the, wow. Gamma rays end about, this is gamma rays. Gamma rays end at about 10 to the minus 15 meters. I see. The gamma rays are stopping at about 10 to the minus 15 meters. You know, we have 10 to the minus 16 meters here. We need to go to 10 to the minus 29 meters. And so what is the shorter wavelength than gamma rays. Cosmic radiation? -29 meters. And so I have a problem here because gamma rays seem to stop here. 10⁻15 meters. This must be maybe a super gamma ray? Super gamma ray. What do you think? No, this must be a calculation error. Calculation. Because do you think your carbon-carbon bonds are going to survive gamma ray bombardment? No. Carbon-carbon bonds will break. They can break. They should break with not gamma. They should break with UV. And so there are two energy scales that we think about. When you're dealing with light, you got to deal with things at two levels. Normally we just deal with things at one level. For example, sugar. When we're dealing with sugar, do you ever worry about, getting one or two molecules too many? You never worry about that. You never worry about the single molecule level. But when we deal with light, we always worry about it. This is not single molecule. This is per mole. When we're dealing with this is single molecule, although light is not single, not mole. And so the first thing is the scale. When we're thinking about these are always kilojoules per mole. Delta H's, delta U's, kilojoules per mole, right? But when we shrink down to a single carbon-carbon bond, well, how many kilojoules is that? And so it takes 347 kilojoules to break a mole of bonds. But if I just want to break one bond, how many kilojoules would it take? Well, we know a mole of bonds consists of 6.022 times 10 to the 23rd bonds. And so what does this number come out to? 347 divided by 6.022 times 10 to the 23rd comes out to 5.76 times
10 to the negative 22.
10 to the negative 22 meters. Okay. Well, not meters. Sorry. Kilojoules per bond. And then what we're going to have is we're going to just have one packet of light. One photon breaks one bond. This is what we call photochemical stoichiometry. And so here we'll have one bond requires one photon of light to break. One mole of bonds requires one mole of photons to break. And so we can have a broken bond here. This photon, the individual photon has to be 5.76 times 10 to the minus 22 kilojoules for one bond. And so what kind of light is that? Well, the wavelength of the light is equal to hc over E, the energy of light. And so let's recalculate. 6.626 times 10 to the minus 34 joules times seconds times 3.00 times 10 to the 8 meters per second divided by the energy, which is 5.76 times 10 to the minus 22 kilojoules, but we need to change that to joules, so it's 1,000 joules per kilojoule down below. And so what does the wavelength come out to? Give it to me in scientific notation.
3.46.
3.46 times 10 to the negative 7 times 10 to the negative 7 meters. What wavelengths do you know? You know 390 nanometers to 760 nanometers. So let's convert it. You know what a nanometer is? A micrometer is 10 to the minus 6 meters. A nanometer is 10 to the minus 9. So if I want to convert this to 10 to the minus 9, I'm going to move the decimal 2 over. So this is going to be 346 nanometers. 346 nanometers, what kind of light is that? This is near UV. This is UV. Will violet break your carbon-carbon bonds? Violet is 390. Will it? No, it's not short enough. And so, in other words, you're safe. If you expose your DNA to visible light, the bond should be safe. If you start exposing your DNA to UV, are you going to break bonds?
Yeah.
Yeah, for sure. Fortunately, this is something I learned in biochemistry when I was taking biochemistry at UCLA, is that your DNA is cleaved by UV irradiation, just being out in the sun 200 times a day. That was a long time ago. That was before the ozone layer was depleted. And so now it's got to be a lot more. But fortunately, your skin cells have repair enzymes that go back and repair the damaged DNA. Have you heard about repair enzymes? Yeah. And so you're still safe. Even if you get exposed to UV and your DNA gets cleaved, you're still relatively safe, I guess. Or are you? I don't know. For how long? But definitely you don't want to expose yourself to too much UV or X-ray or gamma rays, because those will have plenty of energy to do that. All right. So is that enough for today? So we got a little bit ahead, did one problem.